Hi friends, welcome to Ivy-GreGMAT GMAT Quant intro session, Exponents and Roots. Today we are going to cover this important topic, or rather a topic which has got many types, which has got many variants of questions. So let's get started. Exponents. By definition, exponents are shortcut methods of showing a number that has been multiplied by itself multiple number of times. So if I take in any number, say, if I just take any number, say let's take 2. It has been multiplied 4 times. 1, 2, 3, and 4 times. We can represent it as 2 to the 4. Just this becomes 2 to the power 4. Similarly, if I take another number, say let's take 5, multiply thrice, so 5 to the 3. So this is a notation of writing a longer number. So otherwise, we would have been writing, say, let's take a bigger number, say 36 multiplied by 36 by 36 multiplied by 36, and goes on n times. So how to write this? This is 36 to the power n. Simple. So for notation sake, it is represented as e to the power n. That means the number a has been multiplied n times. What do we call a and n? A to the power n. N stands for the exponent. And this a is called as the base. Now we are going to play around with this form only. So better we understand this, that this is somewhat written like this, and we are going to play around. But there is a trick here. So before we go further, let's learn those. Any number a to the power 0 is equal to 1. So that means 2 to the power 0 is also equal to 1. 3 to the power 0 is also equal to 1. 59 to the power 0 is also equal to 1. Or say any number, 1056 to the power 0 is also equal to 1. Or any negative number for that matter, minus 3 to the power 0, minus 5 to the power 0. All these are equal to 1. How it comes to 1 we can derive later on also. But for our simple understanding, any number to the power 0 is equal to 1. And rather, the tricks within the question are laid such that you miss out those things. So we'll come across those questions where you realize that you have missed out this and you have hit the wrong button. So examples given here are 5 to the power 0 is equal to 1, minus 3 to the power 0 is equal to 1, 0 to the power 0 to the power n is also equal to 0. So because however number of times you multiply this number, it stays as 0 only. Now 1 to the power n, that means 1 has been multiplied n times, that is also equal to 1. There is a different notation we have to take into consideration when we are saying that a is to the power minus n. It is nothing but 1 by a to the power n. Any number represented as this, say 2 to the power minus 5. It is nothing but 1 by 2 to the power 5. So this is equal to 1 by 2 into 2 into 2 into 2 into 2 multiplied 5 times. So how to notify this? They came out with this. Now, there is one twist here we'll have to keep in mind. Parts of minus 1. If n is an even integer, then minus the power n is equal to 1. That means if this is an even integer, how the examiner plays around with these kind of things, You'll realize later on how this is a very important, plays a very crucial role. That if this is even, this number remains intact. It is always a positive number because, say, -1 to the power, say, 2. So it is -1 into -1. It becomes 1 because 1 and 1 become +1. Similarly, if n is an odd integer, this is odd. So -1 to the power n, where n is odd, will become a negative number, which is -1. So it's basically -1 into -1 into, say, if this is equal to 3, -1 to the power 3, this becomes -1. So minus minus plus plus and minus minus, so it becomes -1 again. And that stands for every even and odd number. We'll come across this in the later portion of the lecture. Okay. Operations involving the same exponents. So this is same exponents means the top number, this number, n. This is same. So if the exponents are the same, so if I say a to the power n is multiplied by b to the power n, with n being the same, the bottom numbers, the base multiplies, a multiplies by b goes to the power n. Fair? So if I say 2 to the power 2 into 3 to the power 2, we don't have to individually multiply. We have found a formula, or rather an easier shortcut. We can say 2 into multiplied by 3 to the power 2. So if you otherwise want to see 2 to the power 4, and this is 9, this is the 6 square, 9 4 36, this 6 is 36. So rather this notation is easier. So that's why we use this, a to the power n multiplied by b to the power n, where the exponents are the same. The bases multiply ab to the power n. But when they divide, a to the power n divided by b to the power n is nothing but a notation where a by b is to the power n. Let's see again the 2 square divided by 3 square is nothing by 2 by 3 whole square. Do not make the mistake of multiplying, no, thinking it as something else. So whenever this is same, this is going to be the rule. A to the power n divided by b to the power n is actually ab to the power n. Now a bit of a twist. A to the power m to the power n is actually a to the power m into n, or represented as a m n. Another form, or rather, let's take a simple example so that will, because we are taking real numbers. 2 to the power 2 square multiplied by 3 is 2 into 3. Simple. There is a bit of a twist here. A to the power m to the power n, it will become a to the power m to the power n. Not a to the power m n. Clear? So let's see another type involving operations having the same basis. Same basis means we can see this base is the same. A to the power n multiplied by a to the power m. So this remains the same, but these two exponents are different. So same basis, then we do a simple operation. It becomes like a to the power, the base remains the same. The exponents, they add up. So let's take an example. 3 square into 3 to the power 9 will become 3 to the power 2 plus 9, that is 3 to the power 11. Other way around, let's say, if it's dividing with the same basis. So this one, a to the power n divided by a to the power m is actually a to the power n minus m, which is keeping the base same a, and this minus this. To understand it further, say let's say 7 to the power 18 by 7 to the power 9 is equal to 7 to the power 18 minus 9 is equal to 7 to the power 9. Carrying forward this, say 7 to the power 7 divided by 7 to the power 7 is actually 7 to the power 7 minus 7, which is 7 to the power 0, which is equal to 1. Now let us understand why this is 1. So if I multiply 7 into 7 into 7 into 7 into 7 to 7, 3, 4, 5, 6, and 7 times. And similarly, 7 into 7 into 7 into 7 into 7 into 7, 6, and 7 times. This becomes 1. So that's why any number raised to the power 0 is equal to 1. Okay, now fraction of a power. It may so happen that a number a is raised to the power of a fraction. The representation is basically that power rooted over n times. Clear? Simple. So a to the power m divided by n takes a notation something like this: a to the power m to the power n. Here, a bit of a twist here, a bit of a different treatment we are giving here. Let's see how it happens. 2 to the power, say, 1 by 3 is actually somewhat like this. Or let's say 2 to the power 3 by 2 is actually 2 cube rooted over. So it's basically 8 rooted over. So anyway, so these are different ways of notation, but we'll have to remember the basic format in which it operates, so that our calculations becomes easy. So let's see, let's delve a bit further so that our understanding is better. When solving equations with even exponents, we must consider both positive and negative possibilities for a solution. Since so it's saying that consider both positive and negative possibilities when we are dealing with even exponents. That means, since if we square a number, if we square a number, if we say square a number, one second, let me take a bit of any number, positive or negative, the result is always positive. Let's see, say x square, or x to the power 4, or x to the power 6, or x to the power 8. This will lead to a positive number. Whether x is positive or negative, the even square, the even exponents will lead to a positive number. Uh, Going further, 2 square is equal to 4. Then minus 2 square is also equal to 4. So x may be positive or negative. Whether x is positive or negative, the moment I have got this even exponent in place, this even exponent, it leads to a positive number. Hence, if I've got a situation where it is written x to the power x square is equal to 9, it says that x can be equal to 3 or x is equal to minus 3. Both these are possible. Why we are drawing it from this place is because both the things are possible. So let's again take it this way. If minus 3 is raised to an even exponent, say to the power 4, it's basically minus 3 into minus 3 into minus 3 into minus 3. So all these will become positive. So 3 3 is the 9, 9 3 is the 27, 27 3 is the 81, so it is 81. Or say 3 square minus 3 square is equal to 9. Other way around, if x square is equal to 9 and so is 3 square is equal to 9. Both the possibilities are there. So if x square is equal to 9, which means x can be 3 or minus 3. Why I'm timing and again coming to this? Because the questions, they play around with these words, and somehow under time pressure we miss out and we may go for a simple question. So hence, when solving for a variable raised to an even power, a variable say x raised to an even power, we will always get two solutions. Will lead to two solutions unless x square is equal to 0, where x is equal to 0. Fair? Now, while solving odd exponents, we'll get only one solution. Let's say x to the power 3. Odd exponent, if this is given as 8, so x is bound to be 2. X cannot be minus 2. Clear? It's clean. Only one possible solution. While x square is equal to 9 can have two solutions. X can be equal to 3 or can be minus 3. Okay, so let's dig in a bit further. The last digit of the power. So this is one variant which comes. Remember, if xyz is to the power n, it is basically a number xyz multiplied by xyz n number of times, n times. This notation is nothing but z has been multiplied n times. Let's take simple numbers. That will make it easier. If whenever I am saying xyz to the power n, it's basically z to the power n. Say it's, let's take a real number, 784 to the power 784 square. So it's basically 4 square. So 636 is basically 6 square, or 632 is basically, this is the last digit. If I'm asked the last digit, it's basically, if I'm multiplying this number 632, sorry, let's take it this way. 632 into 632, the last digit will be a number, the last digit of the number will be 2 to the 4. So it's xyz square. So it's the last number, z square. So the last digit will be z square. So if it is, say, 634 into whole square is basically equal to 634 into 634, wherein 4 and 4 multiply. So number, the last digit will be 4 into 4, which is equal to 16. So 6 is the last digit. So this is a simpler one. Let's make it a bit twisted, a bit complex. Often asked question is like, a question can be, say, units, digit of uh, 128 to the power 96. Now this follows a simpler approach. You cannot say 8 to the power 96, and that's again a complex thing. Simple step 1. Divide 96 by 4 to find out the cyclicity. Divide it by 4, you'll find 24. 96 by 4 is 24. So the remainder is 0. Now this much, this is the first activity. Step 2 is, if remainder is 0, it is the last digit raised to the power 4, or rather last digit raised to 4. I'll rewrite it again. So in this case, it is, the last digit is 8. So this will become 8 to the power 4. Fair? So 8 to the power 4 is actually 8 square into 8 square, which is 64 into 64. So 4 4s are 16. So 6 is the answer. But what if the remainder is not 0? If the remainder is not 0, then what happens? If remainder is equal to 1, 2 or 3, if remainder is 1, 2 or 3, then it follows last digit raised to the remainder. If remainder is 0, it is last digit raised to the remainder. 2, 4, remainder is 0, then last digit raised to the power 4. If the remainder is, say, 1, 2 or 3, then it's last digit raised to the remainder. You don't have to find the cyclicity that what if it multiplies and 4 times and it actually changes. So that's the thing. So in this question, let's again solve this. This question was units digit. Very common question. So I'm taking it again of say 126 to the power 96. What is the unit digit? Or rather 128 was the, I think, the number. We don't have to multiply 128 or 8 or the last digit 8 to the power 96. No, will not take any of these approaches. The simpler way is, we learned it right now, was divide 96 by 4. Whatever is the exponent, divide it. If it completely divides it, that means the remainder is equal to 0. So by our definition, it is last digit raised to the power 4. Here it is, the last digit is 8, not raised to the power 96, raised to the power 4. So it's basically 8 square into 8 square, which is 8 8s are 64. And this again is 64. So 4 into 4 is 16. So the last digit is 6. Right, folks? So let's go to some questions and solve it. Simpler ones we'll take first, and then we may move ahead with um, a few complex ones. Let's see. 2 raised to the power 3, 4 raised to the minus 3. This is nothing but 2 raised to the 3 into 2, 6 into, this can be represented as 1 by 4 to the power 3. If I look at this, the 4 is actually 2 square. So 2 to the power 6 multiplied by 1 by 2 to the power 6. So this will knock off. Answer is 1. Let's take the next one. If z is equal to 3 to the power 4, then 3 to the power z to the power z into z is what? So let's see. It's z is equal to 3 to the power 4. Then 3 into 3 to the power 4. 4. So what's 3 to the power 4? This is actually 3 into 3 into 3 into 3. It's a 9, 9, 27, 23, the 81. So it's 3 to the power 81 multiplied by 81. So it's actually 3 to the power 81 into 81. Okay, simple. So let's now give a treatment to something like this. 5 to the power 3 plus 5 to the power 3 plus 5 to the power 3 5 to the 3. Now, this is getting a bit more interesting now. So 5 to the power 3 is added up 1, 2, 3, 4, and 5 times. So it's basically, if I pull out 5 to the 3, then I'm left with 1 plus 1 plus 1 plus 1 plus 1. So it's fairly easy, when I pull out the 5 to the 3, it's basically 5 to the 3 into a 5, or rather 5 to the power 1. Do not add up 5 and all these things. So, I mean, uh, a clearer way, let me again do it. I think 5 to the power 3 is basically 1 plus 1 plus 1 plus 1. So 5 to the power 3 is multiplied by a 5, which can be represented as, any number can be represented as 5 to the 3 into 5 to the 1. We know these, when the bases are same, the numbers will add up. So 3 plus 1, 5 to the 4. A similar variant will come, and these kind of questions do bother us in GRE, especially GMAT also. The variation twists a bit with advanced forms. Okay, so let's take the next one. If x is equal to 2 to the power 74 minus 2 to the power 70, what is the largest prime factor of x? Well, now let's give a treatment here. This is equal to, if I pull out or take 2 to the power 70 as common, it becomes 2 to the power 4 minus 1. So this is 2 to the power 70 into 16. 2 to the power 4 is 16 minus 1. So 2 to the power 70 into 15. So 15, if I factorize, it becomes 2 to the power 70 into 5 into 3. So this number, which looks a bit different, the largest prime factor. So if I factorize this, it will be having 72s, where n is equal to 70, multiplied by 5 multiplied by 3. So the largest prime factor is 5. So the largest prime factor is equal to 5. Let's see the next one. Okay. 4 to the power x plus 4 to the power minus x is equal to 2. What is the value of x? So 4 to the power x plus 4 to the power minus x is equal to 2. This is what is given. So let's put our notation in place. 4 to the power x plus 1 by 4 to the power x is equal to 2. Let's solve this. If I take it 4 to the power x, it becomes 4 to the power 2x plus 1 is equal to 2. So 4 to the power 2x plus 1 is equal to 4 to the power x into 2. Now let's play around a bit. This becomes a bit complex looking structure. So let's take 4 to the power x as equal to y. So that will make it easier for us. If this is y, then this is y square plus 1 is equal to y multiplied by 2. Clean? So we are getting an equation here. Y square plus 1 minus 2y square is equal to 0. So this has come this side, which is equal to y minus 1 the whole square. So 2y is equal to 0. So the value of y can be 1. So 4 to the power, if I take it this way, x is equal to 1. Now, the question takes a turn here. As I said, anything to the power 0 is equal to 1. We remember a to the power 0 is equal to 1. So 4 to the power x can become 1 only when x is equal to 0. Clean, right? Okay, the next one. X to the power 5 minus 5 to the power x minus 3 is equal to 124 into 5 to the power y. I mean, let's see what best we can do here. The best way is to simplify this equation. How we can do it? Let's take, this is a smaller number, we can pull this out. So I'll again rub it off, because if 5 to the power x minus 5 into x minus 3 is equal to 124 into 5 to the power y, let's pull out 5 into x power minus 3. This leaves us with 5 to the power 3 minus 1, which is equal to 124 into 5 to the power y. Now this somewhat looks familiar. Maybe we can do something. Let's see. 5 to the power x minus 3 is equal to 125 minus 1 is equal to 124 into 5 to the power y. So 5 to the power x minus 3 multiplied by 124 is equal to 124 into 5 to the power 4. Knock it off. 5 to the power x minus 3 is equal to 5 to the power 4. We've got the same basis here. So x minus 3 is equal to 4. Sorry, 5 to the power y, oh my god, is equal to y. So y is equal to x minus 3. Clear? Let's look at this one. 4 to the power a multiplied by 4 to the power b is equal to 2 into 8 to the power 8 cube altogether. This is the question for us. We can definitely do some simplification here so that it comes in terms of 2. So that will make it easier for us. So we can always say 4 is actually 2 square. So 2 square a is equal to multiplied by 2 square b is equal to 2 into 8 to the power 3, which is again, we can write it at this, we can write as 2 multiplied by 2 cube 3 times. So this is equal to 2 into 2 to the power 9. This is 2 to the power 10. This much we are done. Now let's give some treatment here. 2 to the power twice a into 2 to the power 2b is equal to 2 to the power 10. This is what we have found out. Now once this is done, that means all the bases are same. So twice a plus twice of b is equal to 10. So a plus b is equal to 5. Clear? Okay, the next one. if minus 5 to the power 4x is equal to 5 to the power 9 plus x, and x is an integer, what is the value of x? See, before going ahead, let's go back to the concept. This minus 5 to the power 4x, this will yield a positive value always. This will yield a positive value. So if we are having an equal to and we are having this on the other side, then 9 plus x is also an even number. Even number, that's why it's positive value. To make 9 plus x as even, x is an odd number. So x is odd. So 4x, this 4x is equal to 9 plus x. Clean. The both sides have equal value. So x is equal to 3. How you play around with words or simple gimmicks of number. This is a very good example of that. 3 to the power minus 1 is equal to 2 to the power minus 1. Minus 2 to the power 1, minus 1. 2 to the power minus 1. Okay. Nothing to be squared of all these things. It's basically 1 by 3 minus 1 by 2 raised to the power minus 1. Let's solve this part, then we'll take the reciprocal. It's basically 6. So minus 1 by 6 to the power minus 1, which is minus 6. Clean. Well, now we have got a question here. The units digit of, we solved it in the theories. 3127 to the power 173. Remember what we did here the last time? We divided 173 by, or rather the exponent by 4. So let's divide 173 divided by 4. Whatever the answer is, the remainder is 1. There. 4 4s are 16, 1 3, 4 4 3s are 12, so 1 will be the remainder. Clean. So we remember the rule. If remainder is equal to 1, 2, or 3, it is the last digit raised to the remainder. So last digit here is 7. This 7 raised to the remainder, that's 1, 7. So the units digit of 3127 to the power 173 is nothing but 7 raised to the power 1, 7. So this number will look something like this. Big number, the last digit being 7. And let's move on to the next one. 4 to the power 13 minus 4 to the power 12 divided by 4 to the power 11. Easy. Let's do a bit of a simplification here. 13 and 12, let's hold the years of 4 to the power 12. We are left with the 4 minus 1. Clean. And we are having a 4 to the power 11. which is dividing it. So we can write 4 to the power 12 minus 4 minus 11 into 4 minus 1, 3. So this is basically 4 into 3. Well, this is another one. For xyz is equal to 0 is not equal to 0. Which of the following is equal to this? This looks a bit crooked. It's extremely easy. Xy to the power 3 into z to the power 0 is equal to 1. X to the power 3. Y to the power 4. So this is equal to x to the power 3 into y to the power 3 divided by x to the power 3 into y to the power 3 y to the power 4. This much is understood. I think this much is easy. We are using those basic concepts only. So this will go. This is y to the power 3 minus 4. So this is equal to y to the power minus 1. This is equal to 1 by y. Okay. Now this is the type 8 multiplied to 8 to the power n plus 8 to the power n is equal to 36. Then n is equal to. Let's do a simplification. 8 to the power n. If I take it out, it leaves us 8 plus 1 is equal to 36. So 8 to the power n multiplied by 9 is equal to 36. So 8 to the power n is equal to 36 by 9 equal to 4. 8 to the power n can be represented as 2 to the power 3n. This 4 can be represented as 2 square. So 3n is equal to 2. So n is equal to 2 by 3. Let's go for this one. If 2 to the power k is equal to 3, then 2 to the power 3k plus 2 is equal to what? No. If I look at this part, it is basically 2 to the power 3k multiplied by 2 square. Clear? Now this 2 to the power 3k is actually equal to 2 to the power 3 multiplied by k. Or rather, we can also write as 2 to the power k to the power 3. We know that this is equal to 3. So this is 3 cube actually, which is equal to 27. Now the equation doesn't stop here. We are asked for 2 to the power 3k into 2 square. So this is equal to 27. This is multiplied by 4. This is equal to 108. Many of the smart people may stop here and this is bound to be there in the answer. And you are hitting the wrong answer. So okay, let's see this one. Oh god, again taken in common, but nothing to be frightened of. This looks frightening or intimidating, you can say. This is basically root over 4 to the power 15 into 1 plus 1 plus 1 plus 1. So this is equal to root over 4 to the power 15 multiplied by 4. So this is nothing but 4 to the power 1. So it's root over 4 to the power 16. This is equal to 4 to the power 16 by 2. So it's equal to 4 to the power 8, which is 2 to the power 16. Because 4 to the power 8 is 2 square. So 4 to the 4 is actually 2 square. So this is equal to 2 square to the power 8. So 2 to the power 16. So all those people who couldn't really understand the jump of scale, you will also be doing the same by the end of the sessions. You will be also knowing how to do these simple shortcuts. Anyway, what is the remainder when this number is divided by 10? Well, another variant. So we all know if the exponents are same, a to the power m is multiplied by b to the power m, it becomes ab to the power m. Let's use this here. Look at these 16s. So it's 2 into 3 into 7 to the power 16. So the units digit of this number is equal to 42 to the power 16. So let's see, before when we divide a number by 10, it's basically the number n divided by 10. If I take it like this, it's actually the number becomes, there's a decimal point which moves from for the last digit. So the remainder will be this number only. So if I divide a number by 10, the remainder will be the last digit. So let's see what can be the last digit of this number. So it's basically a twisted question. So to find the last digit, let's divide 16 by 4. It knocks off 100%. The remainder is 0. So our formula for last digit is last digit to the power 4. So here the last digit is 2 to the power 4 0 to 16. So the last digit is 6. So as we know the last digit, so 42 to the power 16 when divided by 10, the last digit is equal to 6. The remainder is 6, so is the last digit. Okay, let's go for the next one. Greatest prime factor of this clumsy looking number. Let's see, 2 to the power 99 minus 2 to the power 96. We can take 2 to the power 96 common. That leaves us with 2 cube minus 1. So 2 to the power 96, 8 minus 1. So 2 to the power 96 into 7. Right? Are we going correct? So that means 2 into 2 into multiplied 96 times into 7. So the largest prime number. Factor is equal to 7. Let's go in for the next one. 2 to the power k minus 2 to the power k plus 1 plus 2 to the power k minus 1 is equal to 2 to the power k into m. What is the value of m? Looks a bit disturbing kind of an equation, but let's make it simpler. Let's pull out 2 to the power k. What remains? 1 minus 2 to the power 1 plus 2 to the power minus 1, which is equal to 2 to the power k multiplied by m. We can cross them off. So it remains is 1 minus 2 plus 1 by 2 is equal to m 2 minus 2 plus 1, which implies that m is equal to, so 1 by 2. Let's go in for the next one. This is something, a question like this can stump many people. Why? Let's see. If 12 to the power x is an odd integer and x is an integer, what is the value of x to the power 12? Now there are two parts to it. Basically, if you look at it, if 12 to the x is odd, it should ring a bell that this is an even number. 12 is an even number. So if I multiply 12 being an even number, 12 is an even number. So if I multiply an even number, say 12 square or 12 4 or say 12 square, 12 to the power 3, 12 to the power 5, 12 to the power anything, any number, 8. The even and the even will multiply and it is bound to be an even number. Right? But here there is a twist. 12 to the power x is leading us to an odd number. How can this be possible? This can only be possible when x is equal to 0, because we know n to the power 0 is equal to 1. Any number x to the power 0 is equal to 1. Reason being, by notation, so 7 to the power 0 is equal to 1, and so is 6 to the power 0 is equal to 1. So odd number or even number, it will become 1. So 12 to the power x can become an odd number when x is equal to 0. So here x is equal to 0. Your question doesn't end here. What is asked is, if 12 to the power x is an odd number and x is an integer, what is the value of x to the power 12? X to the power 12. If 12 to the power x is an odd number and x is an integer, what is the value of x to the power 12? So any number to the power 0, so 0 to the power 12 is equal to 0. We can make a slight change here. If 12 to the power x is an odd number, and that odd number is y, and the question is framed something like, then 12 to the power x is equal to y, then what is the value of x? And what is y to the power 12? So here the value of x is 0. So y to the power 12 will be anything to raise to the power 0 is equal to 1. So y to the power 12 is equal to 1 to the power 12, which is 1. See, the same question, but so deceptive. If 12 to the power x is an odd number, y, what is the value of y to the power 12? Is y to the power 12. So it is not asking you x to the power 12, it's rather asking y to the power 12. So do not get deceived by this kind of thing. So this can always happen. I'm telling you, read the questions very carefully. They are meant to deceive you, or they are meant to put you in a trap. Sometimes you can get stumped, but do not worry. Okay. 125 to the power 14 multiplied by 48 to the power 8 is written out as an integer. How many consecutive zeros? Okay. Will that integer have at the end? So that means that when I multiply these two numbers, 125 to the power 14 and multiply it with 48 to the power 8, this will give me an integer. So xyz followed by 0, 0, 0, 0, 0. So the question here is, how many consecutive zeros are there? To find the consecutive zeros, or the trailing zeros in an integer, the zeros may result from a factor of 10, because 10 into 10 into 10 means there are, so this is 2 into 5 into 2 into 5 into 2 into 5. This will lead to 3 zeros. So how many twos are there? 1, 2, 3, and rather 1, 2, 3. So we will rather take factors of 10. So what are the factors of 10? 2 and 5. So to solve, do the prime factorization of this number. 25 to the power, 125 to the power 14 is actually 5 to the power 3 to the power 14. Similarly, 48 to the power 8 is actually 2 to the power 4 into 3 to the power 8. Okay. So if I take these two numbers, it's actually 5 to the power 3 to the power 14 multiplied by 2 to the power 4 into 3 to the power 8. So this is equal to 5 to the power 42 into 2 to the power 32 into 3 to the power 8. Now this gets a bit interesting here. So minimum number of exponents we'll have to take. One second. Minimum number of exponents. Why minimum number of 2s and 5s we are going to take? The minimum number of 2s and 5, rather minimum number of 2s or 5. Because every 2 and 5 multiplying gives me a 10. But there may be extra 2s or extra 5s, which will not get another partner to make it a 10. So, minimum number of 2s and 5s. In this case, the minimum number of 2s or 5 is 32. So, the number of zeros is equal to 32. Okay, let's go to the next one. Let's see. This question, if k is a positive integer, what is the remainder when k plus 2 multiplied by k to the power 3 minus k is divided by 6? Let's simplify it. K plus 2 into k cube minus k is equal to, if I look at it very closely, k plus 2 multiplied by k into k square minus 1. So this can be written as k into k plus 2 into k square minus 1 square. I'm trying to simplify as much as possible. So this is equal to k into k plus 2 into k minus 1 into k plus 1. Simply put it, it looks just somewhat a figure like it is in ascending order. So k minus 1, this may be the smallest number. This is followed by a k. This is followed by k plus 1. This is followed by a k plus 2. This is, so whatever the number is, k minus 1 plus 1 plus 2. So this is a number, a product of a set of consecutive number. So this, if I look at it properly, this is a product of 1, 2, 3, and 4 of 4 consecutive numbers. So product of 4 consecutive numbers is always divided by factorial 4. So product of 4 consecutive numbers is divisible by factorial 4. So this is equal to 4 into 3 into 2 into 1, which is 24. And this is divisible by 4. So if this number is 24, it's divisible by 6 also. 6 4 is 24. So the remainder is is 0. So what is the remainder when this is divided by 6? Remainder is 0. Clear? Let's go to the next one and see. See how exponents and roots, something that's taking us for a different kinds of questions. Okay. Anyway, let's go for this one. an is equal to 7 to the power n minus 1. What is the units value of a to the power 33? A33, or rather the 33rd number. If I look at this number, this means that the unit digit of 33 is divisible by 4. Let's see. We'll give some treatment to it. A to the power 33 is equal to 7 to the power 33 minus 1. So let me divide 33 divided by 4. When I divide it, the remainder is equal to 1. So the last digit, we had this formula. So it is last digit raised to the power 1 or remainder. So last digit here in this case is obviously 7 to the power 1 is equal to 7. The story doesn't end here. Let us recapitulate. A33 is actually 7 to the power 33 minus 1. So to get the last digit of this, we did our simple formula. Divided by 4, remainder is equal to 1, last digit to the power 1 makes 7 as the last digit. So A33 is a number which has got a last digit which is 7 minus 1 because this is there. So this will become a number where the last digit is 6. See how seemingly innocuous questions can put us off the gear. Many of you will finish here, and obviously this is bound to be there in the answer. You'll click and you'll go ahead. Well, it's wrong. Okay. Right, folks. Thank you very much.